Salting. For foodies, it's a term for adding more salt in their tasteless food. And for travelers, it's a word that reminds us of the salt fields of Kutch in Gujarat, India. Thousands of workers spend their entire lives producing salt. Little do they know that Apache Spark uses the same word to solve one of the distributed computing's biggest problems. In Spark, we use salting for handling data skewness, and strangely, this tiny pinch of salt can reduce a Spark job from 40 minutes to just a few minutes. Engineers borrowed the idea of adding a small random value, like adding a pinch of salt, to distribute data more evenly. Imagine you are managing a massive supermarket checkout line. You have 10 cashiers, which is nothing but your Spark cluster's CPU cores. 99% of your customers are normal shoppers buying a few items. They get evenly distributed across all 10 cashiers. But then, representative of a big hotel shows up with 50 shopping carts filled with supplies, all checking out under one single customer account ID at cash register 1. What happens? Cashiers 2 to 10 finish scanning regular shoppers in 2 minutes and sit completely idle. Meanwhile, cashier 1 gets stuck scanning hotels' endless mountain of items for 2 hours. Your entire supermarket workflow, which in terms of PySpark is a cluster, is still running because of one single bottleneck, eventually increasing the cost. In PySpark, this scenario is called data skew, and salting is the trick where you force hotels items to split up randomly across checkout lines 1 to 10 by handing out fake ticket suffixes, that is, adding salt, so all cashiers can help scan them simultaneously. Now the question comes, what problem does salting solve and what is the impact? See, Spark naturally groups rows with the same key, here customer ID, and sends them to the same partition, that is worker node, during a shuffle operation. If one key has million more rows than others, its assigned partition becomes massive. And the poor worker node handling heavy key tries to load everything into RAM. It eventually crashes and kills your entire job. You must be thinking, Mr. Compylo, thanks for the theory, but how do we solve this in PySpark? Where's the code? Well, code is depicted on your screen now. At first, we have our large transactions data frame containing transaction details. Then we have a much smaller data frame containing customer information. Now, if we perform a normal inner join on customer ID, everything works perfectly and we get all 15 rows in the output as you see on the screen. But what if customer C999 has 10 million transactions? During the shuffle, Spark will try to send all those rows to a single partition because they share the same join key. That's exactly what creates data skew, slowing down the entire job. So how do we solve it? We use salting. As depicted on screen, first you will notice a variable called salt factor. Don't worry about its value for now. We will understand how to choose it later. At first, we will modify the large data frame by creating a new column called salt key. Instead of keeping the key as simply C999, we attach a random number between 0 to 9. As you can see in the output, the same customer now appears as C999 underscore 0, C999 underscore 4, right? And so on. Keep in mind that this is the most important step. we have to effectively split one giant key into 10 smaller keys, allowing Spark to distribute them across multiple partitions instead of sending everything to a single worker. But there is a problem. Our customer data frame still contains only C999, right? Or similar IDs. Now, if we try to join the salt key that we created here with customer key, it won't give any result. And to solve this, we duplicate every customer row 10 times by creating values from 0 to 9 using explode. Then we create the same salt key format on the customer data frame. Now both tables speak the same language. Why did I repeat 10 times? Because the salt factor that I mentioned earlier is 10. Okay. So if you notice, we just created the salt key in large table and similar column has been created in our smaller table to join them. Now if you notice in the customer table, we have created the salt key. And in the final step, we perform the join using the salt key instead of customer ID. Did you notice something interesting here? The output still contains exactly 15 rows what we saw when we used inner join. That means we haven't changed the result at all. We have simply redistributed the workload so that multiple worker nodes can process the heavy customer in parallel instead of making one worker do all the work. It's a very simple technique if you ask me. We are just splitting our customer ID into multiple chunks to improve the overall processing. This is the representation of what our PySpark code did. Earlier, only worker 5 was busy for customer ID with skewed rows. Now, every worker is busy to finish the assigned task quickly so that we can stop the cluster and save dollars. Now that you understand how salting works, the next obvious question is, what exactly is a salt factor and how do we choose the right value? See, the salt factor, often called the number of salt buckets, is simply the total number of random variations or suffixes we choose to create. For example, using numbers from 0 to 9 gives us 10 possible variations. In our example, 10 is just an arbitrary placeholder, which means we are chopping our heavy customer key into 10 smaller pieces. This way, Spark gets more opportunities to process them in parallel across the cluster. Theoretically, you can set the salt factor to any integer greater than 1. These are the common values engineers use depending on the severity of the skew. For small skew, 5 to 10, and for heavy skew, 20, 50, or even 100. See, picking a salt factor is a balancing act. If number picked for salt factor is too small, the skewed workload may still be concentrated in only a few tasks, limiting the benefit. Whereas if it is too large, you will create a different problem, which I call the small file problem. So to decide salt factor, we can use these practical approaches. First is the data volume approach. Let's start by looking at how many rows your heavy skewed key actually has. For example, if your mega customer has 50 million rows and you want each worker node to comfortably handle about 5 million rows at a time, your math would be salt factor equal to total skewed rows divided by target rows per worker. So here, if total skewed rows are 50 million and one worker node can handle 5 million rows, we will get 10 as salt factor. Second approach is the cluster size approach. In this, you should match your salt factor to your cluster's processing power, that is available CPU cores. If your Spark cluster has around 50 executor available, choosing a salt factor close to that number gives Spark more opportunities to process the skewed data in parallel. And finally, we have the approach of trial, error, and monitoring. See, in production, data size changes. The safest approach is start with a moderate number like 5 or 10. Run the job and open Spark UI. Look at the Spark DAG or task details for that stage. If you still see a single task taking way longer than others, your salt factor wasn't high enough. Whereas, if you see too many tiny tasks created, you have probably chosen a salt factor that is too large. In that case, reduce it. But the question is salting still the first choice? No. With modern Spark, that is Spark 3.2 onwards, manual salting is no longer the first choice. It is now considered a second option. So which optimization player took its place in modern Spark? Here is the funny part. Everything we have learned so far is still important, but in modern Spark jobs, Spark can perform similar optimizations automatically. Adaptive query execution, that is AQE, with Skewed Join optimization has taken the crown of salting. In modern Spark, AQE is enabled by default. It watches your shuffle operations at runtime. If it detects that a partition has become heavily skewed, Spark automatically splits that work at runtime behind the scenes. This way, you get the benefit of salting with zero code changes. I know what you are thinking. You must be thinking, is there any scenario when we have to use manual salting today? Or it's a waste of time to learn it? Even with AQE, developers occasionally drop back to manual salting when you are dealing with non-join skews, like heavy group by aggregations. What happens is PySpark's automated skew fixer was built specifically to fix join by connecting two tables. But what if you are not joining tables and instead you are just running a massive group by on one single table? Spark's automatic join skew helper cannot help you here because there is no join happening. And if one customer has 99% of the rows, your grouping operation can become extremely slow. Therefore, you have to use manual salting to break up that single table's heavy group before counting. Let's consider our base table, that is transaction data frame, for this. This is the base data before salting. And just imagine that you have 10 or 50 million rows for customer C999. Now, if you run group by on this, Spark forces every single row belonging to C999 into one worker to sum them up. It works fine currently because it has less records, but it may become extremely slow or even fail due to memory pressure in case we have more records like 10 million or 50 million. And to handle this, we need to follow a three-step process in which the first step is same as what we did for regular salting. Here, we add a salt column by multiplying salt factor with random function, and it will be of integer data type as you see on the screen. In step 2, we group this based on customer ID and salt column. We call this a partial aggregation because each worker has counted only a portion of the data. Instead of one giant group of C999, we now have multiple smaller groups such as C999 with salt 0, C999 with salt 1, and so on. And because we are grouping based on two columns, we are getting the counts accordingly. And in the final step, we group it only with customer ID and sum all the partial counts for each customer ID. But wait, didn't we already count them? So why are we grouping again and this time with some aggregation? Because we only calculated partial counts. If you notice previously, we were counting based on customer ID and salt, not only customer ID. That's why in this final step, we simply add all the partial counts together to recover the original count. One very important point to remember, throughout this video, I am showing worker 1, worker 2 and worker 3 only for illustration. Spark doesn't guarantee that salt 0 always goes to worker 1 or salt 1 always goes to worker 2. The scheduler decides task placement dynamically based on the cluster and available resources. But did you notice that the final answer is exactly same as before? This is our final answer, right? C triple nine has 11 IDs. And let me scroll to the top where we simply did a group by here. Same thing, right? What it concludes is we haven't changed the business result at all. We have simply changed how Spark performs the work. Instead of one worker processing million of rows for a single customer, the workload is divided across multiple worker nodes and then combined back into the same final answer. If you are thinking, why do we still need to know about salting? There are a few valid reasons for this. And the first one is maintaining legacy code bases. Many enterprise pipelines and production systems written a few years ago rely heavily on manual salting. If you need to debug, optimize, or refactor old PySpark jobs, understanding salting is non-negotiable. Second point is edge cases. While adaptive query execution, that is AQE, handles most joins automatically, automated optimizations can occasionally fail on complex pipelines or custom aggregations like group by. Knowing manual salting gives you a reliable tool when modern features fall short. And last point is interviewers love this as a question. Data engineering and big data interviews frequently use salting to test whether a candidate truly understands data skew, shuffles, and distributed computing fundamentals without relying on automated features like AQE. To summarize, salting is a manual PySpark technique used to eliminate data skew by randomly splitting heavy keys across multiple worker nodes. Although modern Spark handles most skews automatically via AQE, understanding salting is still important to handle cases like heavy aggregations and legacy systems. If this effort made salting easy for you, please let me know in comments. So that's all I wanted to discuss in this video. Let's meet you in the next one. Thank you.